Okay, so there we go. Another Friday, another awesome session learning mathematics relevant to quantum. So it's a pleasure to have Maria again with us to on
Thank you.
this journey of reviewing the mathematical tools of quantum mechanics that everyone needs. So without any further ado, Maria, the floor is yours. I will disappear.
Cool. Thank you very much. So this is session 2. So I'm gonna assume that you have seen the first one or you already know those things. If there is something that is completely needed, I will go back over it if I think that is really important. But in general, it should be fine. So we're gonna continue with our introduction to Hilbert spaces. I'm gonna go over notation conventions because I used a convention before that shouldn't be is not the best because it can be lead to mistakes, and a couple of things that I need for them to be clear. Before we move into anything else, I need to remind you what is the cardinality of a set because we're gonna talk about that today. We're gonna do a brief recap from the last session, just so we have things very fresh. And then we're going to proceed to talk about what is orthogonality and orthonormality. That is going to hopefully make clearer what is the basis of a Hilbert space, the dimension of a Hilbert space. And then we're going to talk about separable Hilbert spaces. And I am going to explain what is separability in a wider context, not only with Hilbert spaces. Once we have gone over that, we're going to talk about dual spaces, which is really cool. For that, we need to define what are functionals, and we will talk. I think the coolest result today is the Riesz representation theorem, and that's gonna link with Dirac notation, which I think you will be more acquainted with than I am. But the Riesz representation theorem explain it, so it's good to know that. And then if we have time, which I'm not completely sure, we will go over what are tensor product of vector spaces. We're not going to get into any deeper than that. Not today. So, cool. Without any more dilation, I'm going to start. The closure of a norm of a subset of a set, of a norm set, is written as the subset with this bar. That is, in case you don't remember exactly from last week, is basically the set Y plus all the limits of the Cauchy sequences. Remember that the Cauchy sequences are those that are getting closer and closer and closer. So if a sequence is going to infinity, that one, the limit could be defined as infinity, but that is not included in our closure. The next one is the linear span of a set. It's just the linear combinations of the elements of a set, and is written as lin of Y. And at some point, I'm going to talk about the closure of the linear span of a set. It's going to be just a combination of these two notations. And the most important one is that the calligraphic age is always going to be a Hilbert space, and a Hilbert space is going to always be denoted as a calligraphic age. I've written Hilbert space so many times that at some point I stopped writing it and I just wrote the calligraphic age. So calligraphic age, Hilbert space, nothing else. In the previous talk, I said that it was a normal H, but that can lead to confusion with Hermitian operators. So let's stick with this one. That's all for the notation. It's not a lot, just bear that in mind. And then moving to the cardinality of a set. This is going to be a very loose and brief introduction, but we need to have some concepts clear. First one is the cardinality of a set is the number of elements of the set. And we write it with this absolute value over the set of the set. Two sets have the same cardinality if they have the same number of elements. And if we're worrying about cardinality, it doesn't really matter what kind of elements we have. conventions or things that is worth noting is that the empty set has cardinality 0. There are 0 elements in the empty set. That makes sense. The cardinality of the natural numbers is called countable infinite. You can basically count 1, 2, 3, 4, 5. That's how we define counting with the natural numbers. That's where the countable comes from. Whenever we say that a set is countable, I don't know what happened here. Countable, without saying infinite, we have two options. The A is finite, or the cardinality is countable infinite. And then finally, we say that a set is uncountable. You don't really need to say infinite. It's understood already that it's going to be infinite. Because whenever a set is uncountable, the cardinality of the set is strictly bigger than the natural numbers. So the natural numbers is countable, the real numbers is uncountable, the rational numbers is countable. A closed or an open interval is uncountable. So basically, that's the main idea we need to bear in mind. And now we're going to start talking about Hilbert spaces. Just a small reminder. A Hilbert space, H, is a vector space. We are going to focus on the field of the complex numbers. It has an inner product. Remember that this is a sesquilinear form, so it's linear in the first variable, is conjugate linear in the second variable, and it has some properties that we should remember by now. And it is a norm space, and the norm, it's a very specific one, is induced by the inner product, and the norm of an element is the square root of the inner product of the element of itself. One of the important properties is that the inner product of an element times itself is greater than 0 if the element is strictly greater than 0 if the element is different from the 0 element, if the vector is different from the 0 vector. And it is a Banach space, meaning that it is complete, meaning that every Cauchy sequence, the limit of every Cauchy sequence belongs to the set or to the Hilbert space. A way of imagining that is basically imagining that there are no gaps. So you cannot have holes, tiny holes in the middle of the space. So having that, we're going to start talking about orthogonality and orthonormality. Bear in mind that everything we are trying to do right now is we are taking as an example for example, R2. So in R2, we have vectors, we can add them, we can elongate them, that's multiplying by a scalar. And one thing we can do in R2 is to see what is the angle between those two vectors. Well, now we have maybe an infinite dimension. So we're not going to exactly talk about calculating the angle, but we can talk about orthogonality. We can talk about orthogonality because we have an inner product, and that is going to be the key point to define orthogonality. So we say that whenever we have an inner product space, two elements are orthogonal when the inner product of these two elements is equal to 0. When they are orthogonal, we write it like this. And now we can have a whole family of orthogonal elements. We call it an orthogonal system if the elements are orthogonal 2 by 2, whenever obviously alpha is different from beta. When we also have that the norm of all those elements is 1, so they are normalized, we talk about an orthonormal system. So whenever you see orthonormal, it means that whatever we are talking about, the elements are orthogonal between themselves and they have norm 1. Now, I'm just adding this because in one of the references that I gave and that I'm using, whenever the set in which we are indexing this system is n, they call it an orthonormal or orthogonal sequence. So just bear that in mind if you see that, that's what is happening. This set can be any set. It can be finite, it can be the set 1, 2, 3, 4, 5, or it can be infinite. Cool. So we can have an orthogonal or orthonormal system, but if that system on top of everything satisfies more things, we can have a nicer system. In this case, if the closure of the linear span of this system is the whole space, oh, sorry, this should be H. This should be an H. Then we are talking about a basis. So basically, an orthonormal or orthogonal system that can span the whole Hilbert space is a basis for the Hilbert space. Bear in mind, we have talked, or I'm sure you have seen bases in vector spaces, and what you ask for those bases is linear independence. But orthogonality already implies linear independence. Because if we have two elements that are linearly dependent, so there exists an alpha in the complex numbers, such that we can write one of the elements as a linear combination of the other. When we take the inner product of yx, this is the same as alpha y y, and if we remember, the inner product was linear in the first variable, so we can take the alpha out. And since we're assuming that this is different from 0, then alpha is not 0, and the inner product is not 0. So we don't have an orthogonality between these two elements. So orthogonality implies linear independence. The way we have proven is to see that linear dependence implies orthogonality. They are equivalent statements. Okay, so we know what is a base, but now the question is, do we always have a base? The answer is yes. Whenever we have a Hilbert space, then we can always find an orthonormal basis. In particular, we can start with any orthonormal system and start expanding it until we have a basis for H. The proof of this, I particularly really like it, but it depends on the Thorne's lemma. So in order to do that, I would have to define a lot of not all, but quite some set theoretical results. If you are interested, let me know, because I'm more than happy to either send you resources or go over the proof with you. But we're not going to see it today. But every Hilbert space has a basis. So now I have said that every orthonormal system can be expanded until we obtain a basis for H. So what if we start with two different orthonormal systems? Then we would normally arrive to two different bases. But the linear span of both should be the whole Hilbert space. So there must be some kind of unicity in these bases that we are talking about. And that kind of unicity is going to be given by the cardinality of the bases. So whenever we have two bases for the same Hilbert space, then the cardinality is the same. You cannot have a basis of 2 elements and another basis with 3 elements. If one basis has 2 elements, any other basis will have 2 elements, or countable infinite elements. Every other basis will have countable infinite elements. This is really important because now we can proceed to define what is the dimension of a Hilbert space. Since we know that the cardinality of the basis is not going to change depending on the basis we are choosing, we can define the dimension of a Hilbert space as the cardinality of one of its bases. We choose one, count how many elements we have. That's the dimension of the Hilbert space. So if you remember from the preliminary section, we are going to have finite dimension Hilbert spaces, for example, C to the n. um, countable infinite dimension Hilbert spaces, for example, the sequences of complex elements such that the square of the absolute value of the modulus is summable. And then we're going to have Hilbert spaces of uncountable dimension. In this case, for example, the square integrable function, the space of square integrable function is one example. Now, I'm sure you have not seen that, and you have seen a separable Hilbert space. We say that a Hilbert space is separable whenever it has a countable orthonormal basis, meaning that we have either a finite basis or a basis that can be indexed by n. Why do we put them in the same group instead of keeping that characterization that I said just in the page before? Because when they are separable, so when we are in these two cases, we are going to have really nice properties and they are going to be shared. So it makes sense to have them together and to separate them from those that don't have those properties. Now, this separability comes from a wider context. It comes from, well, topological spaces, but we are focusing in normal spaces. In case somebody is interested or knows about this, a normal space create a topology. And before we talk about separability, I'm going to talk very, very briefly about what is a dense subspace of a normal space. The word dense already tells us that we're going to have a lot of this subspace in the big space E. So basically, whenever we are in E, we are going to have a lot of elements of D. That's what the word dense is telling us in plain English. And that's exactly what it means in mathematics, but we define it formally. How do we define it formally? That the closure of D is the whole set E. That means that for any X in E, we can find a sequence such in D of elements of D such that the sequence converges to X. For example, we know that the rational numbers are dense in the real numbers. So whatever real number that we find, we can that we choose, we can find a sequence of rational numbers that converges to that real number. However, for example, the natural numbers are not dense in the real numbers. We cannot approximate pi by just a sequence of just natural numbers, 1, 2, 3, 4, 5. We cannot put them in any orders and obtain pi. So what is a separable normal space? A normal space is separable if we have a countable subset that is dense in E. So basically, we have a subset D that is countable, is a dimension that we can control more or less, and any element of E can be approximated by sequences on D. This is a strong property. And when we were talking about Hilbert spaces, though, we were talking about just a basis. So it seems like we are losing things in the way. With the next result, we're going to see that actually it makes a lot of sense that we come from this wider context to the orthogonal or orthonormal countable basis. So basically, when we have a Hilbert space and we have an orthonormal basis of this Hilbert space, we can write every element as this infinite sum. These are the coordinates over the vector En, and this is the projection of the vector x over the vector En. And now, the set or dense set would be this orthonormal basis, because we can approximate any element in the Hilbert space by elements of the, well, by linear combinations of the orthonormal basis. On top of that, we have that the norm of the elements of the Hilbert space can be given by this sum of the coordinates. So basically, if we have an orthonormal basis, we can describe every single element, and we can very easily find the norm of every single element. Again, the proof of this theorem is actually really cute, and you can read it. I think you will be able to read it easily. Is in the book written by Nicholas Young, An Introduction to Hilbert Space, in the page 37. However, in order to do that, I would have to prove several inequalities before, and I don't think we would have time in just the 1 hour. If you want to have a look and you have any questions, again, please let me know. So we have seen how useful are orthonormal bases. How do we find one of them? So we have a Hilbert space, and sometimes finding a set of linearly independent vectors is not that difficult. So we have a set of linearly independent vectors, but we want them to be orthonormal. So first of all, we want the norm to be 1, and we want for them to be orthogonal to each other. The Gram-Smith of orthonormalization process give us a way to do that. So we start by taking the first vector, and because it's the first one, we just divide it by its norm. So this is an orthogonal normal vector. To define the following ones, we need to find the orthogonal complement of B2 to B1. And the way of doing that is to take out the projection in the vector U1, which is in the same direction of B1. So we said before that this was the coordinate. This is the whole projection. So if we take this apart, we are going to get a vector that is orthogonal, and we just need to divide by the norm to get an orthonormal vector. So these two should be orthonormal now. And if we continue repeating this process, so if we were to wanted to get U3, we just take B3, which we know is linearly independent, and we just take the orthogonal projection of B3 in U1 and the orthogonal projection of B3 in U2, and we divide by the norm, and we continue like that. A really nice exercise to get quick in calculations, if you want to do that, is to check that actually these vectors defined like this are orthogonal amongst themselves. They are clearly orthonormal. They are clearly normalized because we are dividing by the norm in all of them. So they are all going to have norm 1. But it would be like, if you want to do something and you don't know what to do with your weekend, that could be a nice exercise. Now we're going to start talking about the dual spaces. But in order to do that, we need to first talk about functionals. So what are functional? Basically, a functional is just a mapping that goes from the vector space to the field. In our case, the field is the complex numbers. That's it. Whenever you hear the word functional, they are just telling you that they start in the vector space and they end up in the field. Now, functionals can have properties. So a functional is said to be linear if it's basically what we understand by linearity, so that the image of alpha v plus beta double v is alpha times the image of v plus beta times the image of w for any two vectors and any two scalars. The space of linear functionals is written in this way and is known as the algebraic dual of V. So whenever you read the algebraic dual of V, we are talking about functionals. When you say algebraic, we are only considering linearity. When we have a norm space, though, we can ask for more things. So in a norm space, we have convergence of sequences. So we can define what is for a functional to be continuous on an element of E. So a functional is continuous whenever for any sequence that converges to x, the image of the sequence converges to x. I'm writing this just so we are clearing what convergence means. The elements are in E, so we are using convergence in the norm. The image is in C, so we are using convergence in the complex numbers. We say that a functional is continuous on E if it is continuous on every single element of E. And we write as E star for the set of all continuous linear functionals on the space E. Now, cool things about this. First of all, a small characterization of continuous linear functionals. You don't need to really check every single element of E. When we have a linear functional on a norm space, it's equivalent to be continuous on any single element, with being continuous just at 0, and with the fact that it is bounded in the unit ball of E. So the supremum of the value of the absolute value of the functional in any element of the unit ball is less than infinity. So if you ever need to check if a functional is linear, the quickest way normally will be to check if it's continuous at 0, and if it continues at 0, it's going to be continuous everywhere else. Cool things now. Whenever we have a norm space, the dual is always a Banach space. In order to be a Banach space, we need to define a norm, and the norm that we are defining in the functionals obviously depends on the norm that we had in the initial norm space. How does it depend? Well, we get the norm of a functional is the supremum of the values of the functionals in the unit ball. I'm going to come back for a second. If we remember, we said that when a functional is continuous, this supremum is less than infinity. So we are not doing anything weird. So with this norm defined like this, and the normal pointwise operations, the dual is always a Banach space. Again, the proof is given in the introduction to Hilbert space in page 61. And E star with that norm is called the dual space of E, or the Banach dual of E. Now we can keep taking duals as much as we want. So remember, because E star is a Banach space, we can take E star star, which is again a Banach space. And Banach spaces have a really nice property, which is that E can be embedded in its bidual. By can be embedded, I mean that there is a copy of E in its bidual, and this copy behaves exactly as E. However, for general Banach spaces, E doesn't need to be the same as this should be the bidual, or both of them, the dual or the bidual. So, for example, if we consider the space of all sequences such that they are summable, the dual is the sequences that the supremum is finite, and these two guys are different. They are not the same. Now, when we are dealing with Hilbert spaces, we have a really nice thing happening. This is what the Riesz representation theorem, or the Riesz-Frechet theorem in some resources, says. So I'm going to read it and then I'm going to explain what it means. So when we have a Hilbert space, we have any continuous linear functional. Let's take the one F. And then there will be one element Y in H such that for any other element that we take in the Hilbert space, f of x is exactly the same as if we do the inner product of x and y. What is happening? Whenever we have a continuous linear functional on our Hilbert space, we can rewrite it. It's exactly the same if we write it like this than if we write it like this. This y is also unique, and the norms are the same. Bear in mind that this is the norm in the Hilbert space, and this is the norm in the dual. So basically what we are saying is that they can be identified, the space of the continuous linear functionals and the Hilbert space itself can be identified. And I think I do have some time to talk about the tensor products of vector spaces. So we were talking about linear functionals, but we can actually have mappings that are defined in more than one variable. So when we have x, y, and z vector spaces, we can define a mapping that goes from the Cartesian products of x and y to z, and we say it is bilinear if is linear in both variables. So basically, if the a, this should not be there, a applied to alpha 1 x1 plus alpha 2 x2 y, we can separate it, so we can linearize it and take alpha 1 out times a x1 y plus alpha 2 a x2 y, and we can do the same in the second variable. Again, this should then be here. So a applied to x and b1 y1 b2 y2 is the same as b1 times ax y1 plus b2 times ax y2. That should be a 2. Sorry about that. We write as b of x times y z for the vector space of bilinear mappings that go from x, y to z. And whenever z is the field, we don't write. We just forget about it. Now, tensor products. How do we this? First of all, we're going to define the basic tensor products, which are is an operator that goes from the bilinear forms to the field, to the complex numbers. And how do we apply? How do we find the value when we apply it to a bilinear form? Basically, x tensor y applied to the bilinear form A is the same as A applied to the pair xy. We define the tensor product space as the linear span of these basic tensor products. And this is subset of the algebraic dual of the bilinear forms. How do things look in this space? So I'm just saying a lot of things. When we have an element of this tensor product space, then U is going to have this form. So it's going to be, for now, a finite sum of xy tensor yy multiplied by a scalar, where y is in x and yi is in y for every I. And remember, the way we define the basic tensor products, we had to figure out how we apply them to a bilinear form. Well, how do we apply this U to that bilinear form? It's going to be the linear combination of that bilinear form applied to every pair that creates these elementary tensor products. This representation might not be unique, and that leads to defining the rank of a tensor product U, which is the smallest number n for which there is a representation of U that contains n terms. So if we can write U as a sum of three tensor, as a linear combination of three tensor products, then, and that's the bare minimum we can write. Maybe we can write it as a linear combination of 10 by repeating things. then the rank of U is 3. And an important type of tensor, which are this one that we have defined here, the tensors of rank 1 are elementary tensors. What can we do with tensor products? Well, actually, they are nice because they are linear in both variables again. So when we have x1 plus x2 tensor y, we can separate it. They are linear in the second variable. So when we have x tensor y1 plus y2, we can write it as x tensor y1 plus x tensor y2. When we multiply them by scalars, things work out actually really nicely. So lambda times 1 x tensor y, we can write this as lambda x tensor y or x tensor lambda y. And when we multiply by the vector 0, tensor by the vector 0, we just get the tensor 0. We are all the time talking about linear subspaces and bases. That has been the main topic of this talk. So then for for tensor products, there are nice properties. When we have E and F linearly independent subspaces of two vector spaces, then the set of elementary tensors such that X belongs to E and Y belongs to F is also a linearly independent subset of the tensor products of tensor product space X tensor Y. And whenever E and F are bases, this is also going to be a basis for the tensor product space. I'm going to leave it here for today. I hope things are more or less clear. Again, this is the bibliography. I think this is everything that is going to be needed next week. So hopefully this is going to be a nice introduction for next week. The only new book that I've introduced is this one that is really, really useful to talk about tensor products, mainly the first chapter. Thank you very much for your attention. And if you have any questions, let me know. Yes, can be posted.
Thank you, Maria. I have a question from George. Okay. Question, guys?
Just on the notation, this is actually a challenge. You know, the bracket notation, obviously bracket notation is done by physicists, so nothing to do with the mathematicians. Can you go back there just to, please?
I can go back there. That was actually a bit of a headache.
Yeah.
I didn't know how to.
Is that right? Like a physicist, is it ket? Actually, I think it's the, is it the other, isn't it the other way around?
No, it's right. It's bracket.
Is it? Yeah, but is a cat living in the dual or in the so to start with the star, yeah, this is what opposite. Physicists don't know to the dagger.
It's opposite, yeah.
Yes.
Okay, apologize about that.
Yeah, no, it's okay. This was actually nice for us. This is the thing, because this is, yeah, so that should be the other way around, yeah. Actually.
So the cat lives in the dual.
Yeah. No. The cat lives in the Hilbert space. The bra. Yeah.
Bra is dual.
Yeah, bra is dual. Yeah. I actually have something to share.
And then I might have miswritten that one.
Yeah, it's okay. It's okay. This is because this is a physicist notation, nothing to do with the mathematics. That's why when you are coming from mathematics, it's a very confusing. Maybe I will take the opportunity. This is just, I myself already have a typo, an error somewhere. Maybe Maria can then correct me. I will just share something from my previous sessions. This is just to help clarify those on the audience. I think Max will also cover this later on the thing. So can you see?
Yeah.
Yeah. So this is just for the thing. So for each, so as Maria was saying, on our construction, on our definition of the duals. So what we can do is for each vector in H, we can define a functional from H to the space by making this construction, right? Is this correct, Maria? We can do this, right?
Yeah.
This is linear functional.
Yeah.
Yeah. So this linear functional, this is what physicists call bra. Sorry,
Yeah.
bra. So this is bra. So for each element on the Hilbert space, we can make this construction. So this will be the bra of this. And so the physicists, instead of writing L subscript H, they will put it in place of this. So they call this bra. So this is what they call. So in this construction, so when you see the cat, and you see its bra, it means this linear functional. So this is basically what it think. Just to help clarify more for those of you who have read more like a physicist book. So I hope I didn't make any typo somewhere. And also, the thing, another thing here, as I was saying, this the star, mathematicians write star, but physicists normally they write dagger. So this is the thing. This is nothing to do with Maria. Obviously, this is like a physicist thing, but just to put it into the context. Yeah. So another nice thing to have is that when you have two cats, so basically cat is just a vector, but physicists put it on this thing, on this bracket with the angle. Notice the difference between this and the angle. The thing is pointing that way, basically. Then you can make this construction here, which physicists they write this. So when they write this, they mean is actually what they mean is this operator. This is the thing what they mean. This operator constructed like this, So yeah, this is just the thing, just to not confuse, just to help you, Clara. And actually, I think there's a name for this. Physicists call this construction. They call it the projection operator, I believe. I might myself be confused as well. But yeah, this is just to emphasize. So yeah, so don't worry, Maria. This is we all get caught up with this convention by physicists. It's there. Somehow they are able to do calculations better than this. For me, this is confusion. But Carlos,
I'll try to show
in the next one.
Yeah.
There is this joke that probably is not going to be funny for you, but that as soon as we know that there's something, mathematicians, as soon as we know something exists and is unique, we don't care about anything else. Like,
yeah,
we don't care. So yeah, in this case, in the theorem is like, well, there is a vector and it's unique. So then it's just like, yeah, we're happy with that.
yeah. But somehow the physicists apparently
they need to do the hands-on calculations. So
yeah. So this becomes more convenient, and I think it was Dirac who introduced this, and it became like the standard type of notation for physicists, not mathematicians. So yeah, so I hope it helps clarify a bit for those at home, especially those who have read physicist books written by physicists and this bracket notation stuff. I think Carlos also will probably talk about the cat and bra or something and notation.
We use
So the key to note is that when they say bra, it's just a linear functional. That's it. Yeah. And when you see the bra associated with the cat, is just the linear
inner
functional constructed
the...
out of it. Yeah, that's what they mean. Yeah, when they write that. So for each cat, you can construct the linear functional through the inner product. That's what that linear functional, they write it as a bra. So that's it. Yeah. It's a bit of a headache to get used to. Even me, I get confused as well when it's for a mathematician, is even for someone coming from pure mathematics, this is what a mathematician would call a chess abuse of notation. But somehow physicists are happy to use this. Yeah. So yeah. So
I'm
you can
learning
carry
it.
on. Sorry, Maria.
I'm
to
learning the
crash
right
co-
name.
Sorry?
Yeah.
I'm learning the right name of the things now.
So when you talk to a mathematician, Carlos, don't say bra. Tell them the linear functional instead.
Okay, yeah, I need to take notes.
To be fair, Bra is quicker.
Yeah, it's true. Yeah, so it doesn't have the yeah. Okay, so
You-
sorry, Maria, for crashing your thing. That's it. I
No,
don't know if someone
thank you
else
very
can
much
question.
for correcting that, because I was not completely sure that. Yeah, so it's good. Thank you for catching that
Yeah,
and
no
not
problem.
leaving it.
No
Yeah.
problem. Okay, so does anyone want have any other questions or something that they want to go? We close it for today. You have a lot to review. There's more things to come.
Mhm.
Okay.
Thank
Well,
you.
yeah, in that case, I guess, Carlos, I don't know if you want to add anything. Otherwise, we can just call it a day for people to go and review.
Yeah, no, I'm good. Great. Thanks, Maria.
No worries. So I still haven't used the this thing, Sulip space.
Yeah, I think I invited you. Did you
Yeah.
join?
Yeah, I
Yeah.
did join, but I haven't used it. But I was gonna say is that if for real, if somebody's reading something and you are like, I would need some help or I would like some indications, just send a message through there. I guess I should see things there and I would be able to help.
Okay. Thank you. Okay. Well, in that case, we leave it here. If nobody has any questions, I guess because today not many, because of the people get caught up with the time, and I forgot to send a reminder. Actually, I just sent it 1 hour before the session, so I guess in the next session we'll probably have more people. Let me stop recording so people can be at ease if they want to make a final intervention. If not, we'll just end it here.